Good morning. In our lateral dynamics, so far what we have looked at is moderate or high speed cornering. So when you are driving straight and suddenly you have to go in a turn and you are driving high speed and you are taking a turn, then what would be your vehicle handling response for the required steering input that you are given? Or when you are driving in highway with high speed in straight line, and there is a sudden disturbance that comes from the road or from the wind gust from side of the vehicle, what is the correction of steering or how is your vehicle is going to be behaving, is what is all coming in the moderate or high speed cornering, right? But today's class is a small topic wherein we are going to look at important steering geometry for low speed cornering. So that's what we are going to do it. In high speed cornering, what we have done is we first looked at pure cornering. We had a bicycle model. We are able to have your governing equation for 2-degree freedom bicycle model in the state space form, wherein you defined your body slip angle. So you can also have an expression of 2-degree freedom, not necessarily as lateral velocity and yaw velocity. You can also have rather body slip angle and your yaw velocity. In place of lateral velocity, you can also have a body slip angle instead of lateral velocity. So you see that the derivation also is available in textbook. We did not explicitly do in our class, but one can also have 2 degrees of freedom considering beta and r as 2 degrees of freedom, and you can have this. So in pure cornering, what is the advantage of state matrix that you have understood in finding out steady state responses? Steady state responses, right? We also have to look at now the application of the state matrix in stability point of view, which I will be teaching you after CAT 2 as a separate module of stability analysis, considering bicycle model and considering improved bicycle model. In the sense, if I incorporate my suspension into it, then what would be my stability in case of a rollover stability. So now rollover stability won't be scope of your bicycle model, as it is one rigid vehicle, all mass put together on 2 wheels. You do not have importantly suspension system explicitly, it's appearing in your bicycle model. So you do not account roll effect of your vehicle in bicycle model. So far what we have looked at. But if you have to account roll, what would happen in stability is what is rollover stability. And without even considering roll, even the bicycle model will have an unstable state when it driven in a critical speed of oversteer behavior, will make your vehicle to spin on a plane, and that is also an unstable state. So the stability aspect of your vehicle, we will look at it after CAT 2. So one small topic which is left, which I also thought to be discussed in the class, is as we have looked at our vehicle model in high speed cornering, if it is happened to be a low speed cornering, when is that scenario will come? When you are taking your vehicle and you have to park your vehicle, so wherein you have very low speed and your steering input is very important, so that you will safely park in the lot without hitting the besides vehicles placed there. So you really require your vehicle to listen to you as you give a steering input. But what is important there is like bicycle model, we made a steady state cornering equation considering time varying parameter is 0. The rate of change of time varying parameter like lateral acceleration or yaw velocity rate all made 0. So your simple equation Fi is equal to mru only you have taken. But in low speed cornering, even the centrifugal force is neglected. You are not going to have a lateral acceleration when you are low speed cornering maneuvering your vehicle for parking. In such situation, you will have even the centrifugal force or centripetal force neglected. So it's only the steering geometry very important, with the primary objective of what is that is called reduction in or very less scrubbing of your wheels. So you could see that when you are parking your vehicle, when you are steering, you have sometimes the scrub noise, that is the tire and the road. So the tire will scrub, and that means there will be more wear of your tire. And also you require to give more steering effort. But if that scrubbing of tire is eliminated, that means the scrub radius, the contact is very minimum or not appearing. That means you will not have wear phenomena. Also, it become ease of steering. So this is the primary objective with which your steering mechanism in your vehicle is designed, right? One such a steering mechanism geometry is what is popularly called Ackermann steering geometry. So today we are going to look at what is the Ackermann steering geometry, how that elimination of tire scrub can be met, what should be theoretical design of your steering mechanism in order to improve the less effort steering or no scrubbing of your tire on the floor, what to do, what is that geometry recommended is what we are going to essentially see today's class. Maybe that will be over in 20 minutes also. Then we will have some instruction for CAT 2. So with that, let me share my screen and go ahead teaching today. Hope all of you are able to see the screen. Today's lecture number 27 and today's date 11/9/2020, and today's topic of discussion is low speed cornering. What is important assumption or what is important statement in low speed cornering is your centrifugal force is neglected, right? Your centrifugal force is neglected. It is to minimize scrubbing of tire and to improve steering effort. So this is what is that important objective that low speed cornering vehicle has to be designed, and we are going to look at what is called an Ackermann steering geometry. Right. So what is this Ackermann steering geometry recommends? So if you have to meet minimum scrubbing or improved steering effort, when you are doing a low speed turn, your wheels should turn with respect to a common center with a different radii. That's what is the requirement. So you have in a vehicle all four steel steering or front wheel steering mechanism and so on. So we are going to take a simple fixed beam front wheel steering mechanism, and that whatever the approach that we are going to look at today can be the same but much involved approach of for example independent suspension front wheel steering system. So then the approach is the same, but what is that approach is the same. What is the error actually present in your steering system? Though this Ackermann steering system geometry we are going to look at it, that is the theoretical geometry. But in reality, in your vehicle, you can't achieve that same theoretical steering geometry. There can be some error involved, and that error is what is going to cause scrubbing of tires. But minimizing that error is what people are working, and that error prediction is what I am going to explain you today. And the error prediction will be easier to understand on today's lecture because I am going to consider steering wheel geometry with the fixed front beam axle. If it is happen to be independent, you know the steering system geometry, or we will see later, or we can refer to some textbook, the steering mechanism, how does it function and so on. So independent suspension steering system essentially may have your what is called rack and pinion arrangement with outer tie rods, or you can have instead of single tie rod piece which is required for a coplanar fixed beam steering system, maybe it will be replaced by a number of tie rod pieces and so on. So the geometry will essentially only will change, but you are going to have the approach of finding this steering geometry error from Ackermann steering geometry, which is theoretical, is what we are going to look at it. So for that, let me look at now what is this Ackermann steering geometry. First, let me define that. So for which I am going to look at the vehicle top view, and I'm not going to look at body, only the axles. So these are the two rear axle. These are the these are the two rear wheels and with the axle. And what is this distance is called track with B. This is called a track. Like a wheelbase, you say, which is now I'm going to draw. This is a wheelbase L, and this is what is called a track, or it is also called a tread B, right? So that what is that now I am going to have here is this front wheel steering mechanism. So these are rear wheels what is drawn now, and front wheels will be drawn now with a given steering angle. Say this is the steering angle. So when I draw the steering angle, you know the turn is in this side, and this is inside, inner side, and this is outer side. So this is outer side, and this side is inner side of the turn. And you see your steering angle will be more given in the inner front tires compared to that of this, in order to meet the requirement of this Ackermann steering mechanism. What is the requirement is this all four wheels should turn about a common center. Say this is the center. So you see with the different radii. So for this wheel, this is the radius. For this wheel, this is the longer radius. And this wheel, if I connect to this, perpendicular, right? Because this is your steering angle now you are given. If this is your heading direction of your vehicle, this is steering angle given now, which is say delta I. And there is a steering angle here. So if I draw the perpendicular and connect to this, so this is what is now the steering angle here, right? So this is 90 degrees. So now what is this angle given here is delta naught. So there is a relationship between this delta I and delta naught. If they are same, then it is called a parallel steering mechanism. But the Ackermann steering mechanism is not the one which is parallel steer angle of this front and rear axle. Why? Because to meet these two objectives, you should have these all four wheels are turning about a common center with a different radius. So this radius is different, this radius is different, this is different, this is different. So this is what is recommended theoretical one. So now you see this line is what is the line joining mid of the front axle and mid of the rear axle. So this intersection with see now let us call this point as M, right? And then join in this geometry to understand. What is this geometry to understand is this. So there is two angles here, they are not the same. Inner wheel steer angle is more than that of outer wheel steer angle. That's very clear here as well. So this angle is what is delta I, this angle is what is delta naught, right? So what is the relation here exists? It is cot of angle delta naught minus cot of angle delta I is what is this B by L. B is track, the axle length, and L is wheelbase, right? So this is that equation which is corresponds to. If this relation holds good, this geometry is what is called an Ackermann steering geometry. So this can be easily proved, and how is it achieved is what I'm going to explain you. So for that purpose, let us now look at the midpoint of the front axle to be connected to the contact patch center of the rear inner wheel. So I'm going to connect this line. So when it is joined, this is going to intersect the line produced from this point. So let us name for convenient. Say this point is C, this point is D, this point is E, and this point is F. So I have joined MF, and that is intersecting the line produced from D at right angle to this steer angle to meet the center of turn. And this two intersect at a point. Say this point is Q. This point is Q. Of course, now what is CG location of your vehicle? Somewhere here. We consider this is my CG location. The vehicle is going to turn with respect to CG is what is the radius of turn R, which we are looking at in bicycle model and so on. This is radius of turn of your overall on the entire vehicle. And if you look at what is that thing at any instant of your turn, this is an instantaneous center. So these are all points in this rigid vehicle. If we connect, you will have the respective velocities at right angle to these points. So now this wheel angle here, what is this delta naught, delta I. So you may say that delta naught, delta I, this is your actual orientation and wheel travel also. You will not have here a slip angle. That's what is important. There is no slip angle here. That is what is an important assumption, that no centrifugal effect, no centrifugal force. Consider as it is low speed cornering. So when there is no centrifugal force, I neglect it. I neglect there is a lateral force requirement, and that is essentially lateral force. You know that it is because of C alpha into alpha. So when no centrifugal force, this is zero, and there is no slip angle. So it's only the steering angle in low speeds. Right, so we do not worry about the mechanism of development of slip angle and so on. That's all needed when you are going for high speed cornering. So now continuing with what we are doing is, we just connected this midpoint of the front axle to the inner side rear center contact patch center point F, and this point is Q. So now this line MQ FQM line is very important line, right? Okay, that's one thing. Now connect this Q to point C. Connect this Q to this point C. Let me do that. Let me take the same color. Connect this to this point C. Right. And let me also drop a perpendicular from Q to this CD. This is a perpendicular. This is perpendicular. So let this point be now. Let this point be now A, point A. So I have now triangle QAM and I have triangle FCM. These two triangles are similar triangle. That you have to understand. And now this MA. What is this MA? Is sum of the distance now. So let me call that distance as small e1 or e2, and AQ, this distance AQ as e1, right? E1. If that is so, see also here it is 90 degrees. So if this is delta naught, what is this angle here is? This angle is delta naught. Now you connect this point C to Q, and the angle made by QC to this vertical is also, this angle is delta I. So now if this is so, you can prove this relation 1. What is that we have written very simply? What is that you have to do? The angle MCQ, this angle MCQ is what is delta I. That is what is delta I. Angle MCQ is what is delta I. Right? So now it's a simple trigonometry relation. So I can find what is cot delta naught and what is cot delta I. Looking at the triangle. So look at the triangle DQA. What is cot delta naught? In triangle dqa cot delta naught is adjacent side by opposite side. Tan is opposite by adjacent, cot is adjacent by opposite. So adjacent is what? A dA by QA. dA by QA. What is dA? It is B by 2 by plus E2 by E1. Right? So this distance is B by 2 of the track. So dm is B by 2, MA is E2. So B by 2 plus E2 by E1 is what is cot delta 1. What is called cot delta I? Cot delta I is this triangle CQ ACQ. In triangle ACQ, what is cot delta I is adjacent. Adjacent is B by 2 minus E2 by opposite E1. So now if these two relations are understood from a simple right angle trigonometry, you get your one proved. Substitute them in this, you get B by 2. What is that you'll get? It is going to be cot delta naught minus cot delta I is going to be 2 E2 by E1. That's what you get when I substitute. So what is this E2 by E1? So E2 by E1 to get, I am going to look at the similar triangle. E2 by E1 to get, I am going to look at this similar triangle. What are the similar triangle? MQA and MFC. In that triangle, you have these are the two triangles. So that gives me the relation E2 by L. E2 by L is what is E1 by L. E1 by L is what is E2 by B by 2. So this gives you E2 by, I needed E2 by E1 in terms of B and L, so that I can replace it here. So E2 by E1 is what is going to be B by 2L. B by 2L. So if I substitute that here, 2B by 2L, 2 goes, what is that I get is B by L. Simple proof of equation 1 is proved. So this geometry, what is that I have just explained, is what is called an Ackermann steering geometry. So if someone asks you what is Ackermann steering geometry, you should be able to explain this with the steering angle delta naught and delta I of outer and inner front wheels angles. Then that's equal to the ratio of wheelbase to track by wheelbase. So this is what you have to explain. So this is your Ackermann steering angle. So now how do you get graphically this? What is the error involved? So if this Ackermann steering angle is made in a given vehicle, you will have your variations. For example, let me just compare this variation of steering angle. Now let me take on x-axis delta I, y-axis x-axis delta I, y-axis delta naught. Say for example, I take still 40 degrees. Because low speed turn, you may have more angle turn. In high speeds, you will not have this much degrees. What is that angle that you have seen? Steer angle. It will be hardly of 5-6 degrees maximum. Right? So now this is what is your parallel steer geometry. When you have delta I, that's equal to delta naught every time. That's parallel steer geometry. How Ackermann steer geometry defined with respect to that is what we are seeing, and that would be this. Ackermann steering geometry is this theoretical one, which is not linear like this, but it will be varying something like this. It will go something like this. And then what is with the error, if you look at, that's going to be in between this. This is with error. This is the error curve with the error. This is Ackermann. Ackermann steering geometry, and this is parallel steering geometry. Parallel steer geometry. So this variation, how do you get is for that only I am going to consider now front suspension or fixed suspension. It's not an independent suspension, fixed beam suspension, and I have my steering geometry there. is the planar steering geometry for simplicity. So let me draw the top view of my contact point rectangles. Contact point rectangle. So this is my track and this is my wheelbase. I have to first construct this, what we have just now seen. So if I construct this point, which is C, this point is D, this point is E, this point is F. If I take a turn on this side, so this is going to be my inner side, inside, this is outer side. If that is so, now what is my steering geometry? My steering geometry is planar steering geometry. That means I'll have steer arm and tie rod. Steer arm are this. So this is my steer arm. Let me draw that. This is my steer arm. And this side it is. This is my steer arm. And I connect this by a tie rod. So this is tie rod. These two are, so CH let me call, this is DI. So CH and DI are steer arm. Right? And HI is what is tie rod. So this is simple 4-bar linkage. So where DC is fixed and these two are like two crank, and this is your connecting rod in the mechanism. So now, why did I draw this? Is what is Ackermann steering geometry? Is if I take this midpoint M and the inner side rear tire contact patch, and if I connect this, if I join this, I should have my, of course, this is your wheel, your vehicle axis. So you will have the point Q lying on this, but now it is not so. So now what is that we will do? We will take the steering now given in this side. So let me draw now my steering geometry change graphically. Maybe say I will give this 30 degrees now, right? So this is my orientation of my steer arm CH. So if this is 30 degrees now given, and now correspondingly, what is the change here? This will also go in this circular arc I will draw, and take this tie rod distance. This is a center, cut an arc on this. So you will have, this is what is your change in orientation of your tie rod, and the corresponding change in this DI steer arm. So this is the change when it is from 0 to 30 degrees, say, for example. I'm taking that angle now in increment. I'm going to see that is it going to have any error. So what is that I should do now? Let me take some increments here. This 30 degrees, I'm going to change it as 10 degrees. Another 10 degrees, like that. So this is 10 degrees. And this is 20, and this is 30, right? 20, 30. Now, how am I going to get this like this? So what I should do, I have to locate my point Q. Is it lying over here? So what is that Ackermann steering geometry says? I will have my steer wheel angle here, delta naught to this and delta I to this. So if I plot this 30 degrees now from here, see, if I draw that, I produce a line which is 30 degrees from here. So this is now 30 degrees. I have produced this line, right? And then again from here, what is that corresponding? I'm not taking this is 30 degrees, so here it is 30 degree turn. I just measure now, because this is going to be greater than this. That's what Ackermann steering geometry that we have seen. Delta I is greater than delta naught, right? So what is the corresponding delta naught is what I am measuring here. So if I have that and I take that and then draw from here. So when I draw that, if I extend this line, if I extend this line, If these two meet at this point, there is no error. In case it is not meeting, it is meeting some other point here, then that is an error. So meeting here is Q, no error, but if it meets here, it is say O3, just 30 degrees. So if I take 10 degrees now, but then the corresponding value is, in this arc, I have to take from this point, I have to cut an arc on this, and that is what is now orientation corresponding to 10 degrees, and I will have here corresponding delta naught. So this angle I should take first, and then I should draw from here. If this is with the Ackermann steering geometry, that will meet on line MF. If not, it will go here. So this is a point O1. Similarly, I get point O2. So this is all with the error. It is not lying in this. So this error is inevitable, which will be there in your real time. And with that error, if you look at, for the given steering angle of inner wheel during the turn, will have a corresponding outer wheel turn with some error involved. So that is what is given by this. And this error is minimized. So you will be able to have minimum scrubbing of tires and lesser effort required to turn. So this is what is the simple approach of finding out the error in your actual vehicle. Once the system is employed, what is the error present? So this error can be corrected in order to meet your tire scrubbing, right? So this is what is a simple approach. So this approach become more involved if I do not have this coplanar system of steering geometry. So my steer arm and tie rod all are in one single pane. If that is not going to be same in case of your independent suspension. So your independent suspension may have what is the rack and pinion arrangement or number of tie rod pieces. Then the approach is similar. Like you give an inner side steering angle, what is the corresponding outer side steering angle? But your mechanism, what you draw graphically, is going to be involved. So graphical approach is simple. You could have studied in mechanics of machines course. You had what is that, Freudenstein equation. So if you are giving some range of input for the crank, what is the range of output of that you are able to synthesize? So you are able to come out with the dimension of your connecting rod between that mechanism. So the same essential kind of approach is required to synthesize your mechanism of steering, right? That is what is this. I have just taken a simple 4-bar mechanism of your steering system, which is commonly used in a vehicle of fixed beam front axle, maybe van type vehicle. So this is applicable. So this is what is called a low speed cornering, and the main objective in low speed cornering is that your vehicle should have lesser steering effort needed, and the tire should not wear because of scrubbing of tire on the ground. So if you have understood this, we have done now low speed cornering, moderate high speed cornering, steady state cornering study. And if it is not steady state cornering, you have your yaw velocity rate also accounted, then you have also looked at pure cornering. But what is that we have not looked at is during cornering, if you are accelerating or braking, what would happen? That we have not looked at. If you have to look at it, instead of bicycle model with the two equations, you should also require an equation which is Fx equal to U naught minus MRV, which is not we have seen in that, right? So there are three equations for a ground vehicle. Two only we have looked at so far. What was those? So Fy is equal to M into V dot plus MRU, and Mz is equal to Iz R dot. So these are represented in a bicycle model. You had a state matrix A. But if I consider acceleration or braking, then Fx is equal to mu dot, this is u dot, minus Rv. So this equation we have not considered. So this equation, if we consider, that is more involved dynamics. So with that note, let me finish today's lecture.